Hello, this is Philip Myers of PEMI Consulting. In case you missed the API 2020 Storage Tank Conference and Expo given in October of 2020, I'm recording this presentation so that you can see the talk I gave. It's about API 2000 pressure vacuum vent valves, often called PV valves, and the most recent flow certification work that has been conducted. Although the title is Flow Certification of Venting Devices, I'm going to spend about half of the time on API 2000 itself, its background, purpose, scope, and how it is a standard divided, and what you should know about it. The link at the bottom is a resource that has all of this information and much more. It's a public repository on Github, and you can download the data files, the code that was used to develop the analysis of variants showing what's going on with the testing data, white papers, and so forth. The scope of API 2000 is much broader than just for API 650 tanks. It not only covers ASTs, but USTs, or underground storage tanks as well. It covers refrigerated, heated, and of course ambient temperature tanks. It covers all petroleum products. The pressure range goes from a full vacuum to 15 psig, so it covers API 620 tanks as well as spheres that are operating at or below 15 psi. Although LNG is currently out of the scope, our committee is looking at including it in the near future. The fundamental purpose of API 2000 is to keep the pressure of a container or tank within its design limits. It does this for two cases: normal and emergency venting. We'll define these terms a few slides from now. Tanks have large surface areas and therefore are subject to large forces when there is too much pressure or vacuum. These tanks suffered too much pressure. The same idea applies to excess vacuum for these containers. Normal breathing is defined as the amount of air needed to make up for displaced liquid or temperature changes. When liquid is pumped into a tank, the air that is displaced must be relieved. Similarly, when it is pumped out, air must be let in or a vacuum will develop. You know from high school that gases expand when heated, so when the morning sun shines on the tank, the air and vapors will grow in volume and they must be relieved. When there is rain or cold, the heat flows out of the tank through its surfaces and the volume of gas shrinks, so air must be let in to avoid a vacuum failure. I'll explain emergency venting next. Most tanks are in facilities that handle combustible and flammable liquids. Hence, they are subject to the heat from an adjacent fire, where if another tank is on fire or there's a ground fire or some kind of pressurized jet fire, the radiant and convective heat can cause expansion of the vapors, leading to a dangerous overpressure situation unless gases are relieved at a sufficient rate. This is the purpose of emergency venting. A word about flame arresters required on tanks. This quote comes from API 2000. The petroleum industry has had good experience with tanks protected by pressure and vacuum vents without flame arresters. As a result, there has been a belief that this good experience is due to the pressure vents' potentially inherent flame arresting capabilities. Recent testing, however, disproves this hypothesis, at least for the tested conditions. There are two ways to satisfy emergency venting requirements. First, there are specifically designed devices as shown on the left. Second, a frangible roof or a weak roof to shell joint, which is only applicable to tanks larger than 50 feet in diameter. Here is a summary of all the points we've talked about so far. All tanks are subject to API 2000 requirements. Tank pressures must be kept within design limits under both normal and emergency conditions. Two different types of venting are addressed: normal venting and emergency venting. The 7th edition of API 2000 is the worldwide consensus standard on tanks. Every regulation, including OSHA, NFPA, PEI, STI, etc., uses and is based on API 2000. For more information and 3 excellent videos on the details of API 2000, Google PEMI Consulting YouTube channel or use the link below. There are 3 excellent videos that go into the computational details of API 2000. Earlier, I called API 2000 a standard divided. It is divided into what is called the main body and the annex. When the 6th edition was coming online, there were efforts to harmonize some of the differences between EN 14015 and ISO 28300. The result was 2 standards in one. The 5th edition was put into the annex, and the newer material was put into the main body. The main body is more up to date and has more accuracy in its computations. However, it is also more difficult to do the calculations because more input information is required, as we'll see on the next slide. The difference between flow calculations for a given tank, depending on whether you are using the main body or the annex, can be significant. It's important to note that there is no change to the emergency venting calculations. Just to give you a visual graphic of the differences between the main body and the annex, you can see that these little boxes here, there's about twice as many inputs required to do the main body as to do Annex A calculations. There are a few other differences that are shown below. So hopefully, if you are not already familiar with this, you are asking the question, should I or do I have to use the main body or the annex version of API 2000? Unless a regulation specifies the API 2000 edition and whether or not the annex must or must not be used, then you are free to use either the main body or the annex. I recommend that you use the main body for new tank when major tank work is being done, and that you use the annex if it would require you to retrofit or modify existing tanks. So the rule of thumb is use the annex for existing tanks, but use the main body for new tanks. This is, of course, entirely your company's choice, but each company should articulate its policy on this topic in the form of written guidelines or internal standards. Here is the point in the presentation where we transition to the work of the Flow Certification Task Group. For background, this is the certified flow curve. It's typical of manufacturer certified flow curves. On the x-axis, we have the airflow in thousands of standard cubic feet per hour. On the y-axis, we have the tank pressure, which is also the inlet pressure to the venting device, usually in inches of water column, or OSI, ounces per square inch. But why are we concerned about the accuracy of these flow curves? The consensus of manufacturers was that there are some who do not play by the rules and who have outrageous claims. The statements above show that exactly what manufacturers are saying about their flow certifications. These statements are all over the map and are definitely not standardized. This and the next 2 slides were shown to the API 2000 committee, who decided that the issues needed to be studied further by the task group. I won't go into detail here, but simply note the very large differences in claims about flow rates for a 12-inch vent valve with exactly the same set point. The real question is, should the flow rates be independently and third-party certified? Knowing the flow rate curves accurately is important because both PV vent valves and emergency venting devices guard the mechanical integrity of tank systems. Recall that the 5th edition of API 2000 was the single edition of the venting standard prior to it merging with EN and ISO. That required a test setup for manufacturer certification, as shown on the left. See that the PV valve is mounted on the top of tanks, which have different configurations. From the 6th edition onward, the test setup on the right was specified. We don't have time to get into the details of the differences. For that, you can go directly to API 2000, but we will refer to the old version as the 5th edition rig and the new version as the 7th edition rig. It turns out today that about half of the manufacturers use the 7th edition rig and the other half use the 5th edition. Why isn't everybody using the 7th edition rig? After all, it should be more up to date. The answer is that it's costly to switch over test rigs, and there are many who believe that the 7th edition rig is inferior to the testing specified by the 5th edition. So another question is, does the rig make a difference in test results? We settled on doing the simplest possible test to determine if the testing rig makes a difference. So how do you do a test in the simplest possible manner? Well, you replace the PV valve with an orifice here. So the test rig is sitting down here and the orifice is added just above it. That eliminates the complexities of not only the manufactured device but also the variable area of this pallet. You can see that this test is much simplified and is really just testing the ability to measure flow through a fixed orifice given a particular test rig. Here is a drawing of one of the orifices that was used. Each participating manufacturer used the same set of 3 orifices in the test. In other words, after the testing, they shipped it to the next manufacturer for testing. This eliminated possible variability of slightly different orifices. One should probably expect the difference to be reflected only by the 5th or the 7th edition test rigs, but one should also expect the same results for everyone using a particular test rig if the current testing is accurate, right? Here's the raw data from vendor E. Each vendor received the same 2-inch, 6-inch, and 10-inch orifices in turn and tested at pressure differences of approximately 1, 2, 3, 4, and 5 inches water column. Each vendor was expected to report 30 flow rates consisting of 3 diameters, 5 pressures, and 2 modes, where the mode was pressure or vacuum. None of the vendors submitted complete data. However, 4 vendors, A, B, E, and F, gave us complete data sets on pressures 2, 3, 4, and 5 inches of water column. So we had 96 observations from 4 vendors, 3 diameters, 4 pressures, and 2 modes. 48 in the pressure mode and 48 in the vacuum mode. The data from only 4 vendors turned out to be viable. For them, the flow measurements were substantially different as shown by the first bullet. Because of the simplified testing protocol, the error for individual devices would be much higher. There was no particular correlation whether the 5th edition or the 7th edition test rig was used. This was an informal analysis. A little bit about how the analysis was conducted. A formal technique called a factorial analysis of variance, or ANOVA, was used. We can't get into the details, but if you Google ANOVA, you can learn about it. This type of analysis partitions the contributions of the various types of error terms into contributions by the various factors. Obviously, diameter and pressure make a big difference in the test results, so you get a p-value of 0 for them as shown. The p-value is a statistical term indicating if there is a significant effect resulting from a particular test factor. The third significant factor is shown as V for vendor. This means that the vendor was responsible for the test variability. The basic message is that vendor bias or error in measurement is significant and it is real, even for this dumbed-down version of testing. On another note, a repeated measures ANOVA would have had to have been done to quantify the effects of using test rig 5 versus 7. Unfortunately, because repeated measures were not made, it is not possible to partition the variability associated with the test rig. However, in looking informally at all 6 data sets, there was no clear pattern showing that the test rig version had any systematic effect on the results. The repeated measures ANOVA should be done when the test results are repeated under more formal conditions, hopefully at the blessing and discretion of the API 2000 Leadership Committee. This table shows a percentage of deviation from the average group estimate along with margins of error at the 90% confidence level. Because we did not have funding and the testing was not expected to show these discrepancies, we did not have a gold standard. A gold standard is the best and most accurate way to measure a variable. For example, a gold standard for air flowing through a testing device is to collect all the air that passes through a device in a large bag or container and to weigh the mass of air. Obviously, the gold standard costs much more than the kind of measurements we used. The bottom line is that we can determine how far each vendor deviates from the average, or what I call the consensus flow, but we don't really know what their accuracy is. Of course, if the vendors vary significantly, then at least one of them must be inaccurate. This diagram shows the total noise, which is the measured flow rate minus the consensus flow rate, which is used as a proxy for the gold standard. Total noise has three components. First, vendor by diameter. Second, vendor by pressure bias. And third, pure error or random residual noise after accounting for the bias. The horizontal axis shows the nominal orifice diameter as major ticks and nominal pressure difference as minor ticks. Solid symbols are noise, whereas the dotted lines are vendor bias. The vendor bias stands out above the noise, which is what it means to be statistically significant. I will simply say that vacuum measurement errors had a similar magnitude of error from the consensus flow, meaning that both pressure and vacuum flow certification is at best inaccurate and possibly unreliable. The next steps are uncertain and unknown. They are up to the decision of the leadership at API 2000. Our analysis has been transparent, based on the data, and reproducible. You can get the several white papers that have been written, the complete data sets, the codes to do the ANOVA, and most importantly, the white paper that we've written from Github at the link shown. I'd like to acknowledge George Woodworth, who did the statistics, and Andy Wong, who helped with the graphics. Thank you.